iodide through a bimolecular, intermolecular, if you will, SN2 reaction. This alkoxide could displace that iodide through an intramolecular SN2 reaction. Do you remember what we said last time? Which type of reaction, generally speaking, is faster, the intermolecular or the intramolecular? Intramolecular, because everything is right in there. So we anticipate that because proton exchange processes of the sort are very, very fast, much faster than anything else, the proton exchange, we are setting the stage in here for a competition between a bimolecular SN2 and an intramolecular SN2. Which one is going to win? The intramolecular. Obviously, it's much faster. Typically 100 times or more faster. So, we anticipate, based on everything that we have studied in the past, that this reaction, being so fast, it is going to promote an intramolecular SN2 displacement of the iodide, like such. This is an SN2 step now, an intramolecular SN2 step, leading to the formation of a product in which this oxygen obviously has become bound to the carbon. We have created some kind of an ether. You recall that a compound of this sort is called an ether, to the extent that we have an oxygen, bridging a pair of alkyl groups. That's an ether, right? That's what we expect to happen. And that's exactly what does happen. So there it is. That's the product of this transformation, right? And on that note, we have concluded worksheet 11. It's done. We may now go on to worksheet 12, which I am not going to do, however, in the order proposed to you. I'm going to alter the order in which we're going to address the various problems. And there is a very valid reason for that. We're going to start with problem number 4 in the worksheet. Why are we going to start with problem number 4? Because this problem number 4 is extraordinarily similar to some of the questions that have appeared in the previous worksheet. So, while that stuff is still fresh in our mind, let's dismiss these very, very, very similar questions, and then we'll go on to more, perhaps interesting matters. So, let me go ahead and put the central projector back on PC so we can see it. Let's see what is going on in here. We are told that this particular molecule, this enantiomeric form of this molecule, is caused to react with that thing. Have we seen this before? Yes or no? Yes. And what the hell is that? That's LDA. And what does that do? That's your molecular dentist. It pulls not teeth, but protons. All right? Right? So it pulls protons. And if we see that, automatically we know that there must be some kind of a proton that is going to be pulled away from a molecule. Right? Are there any protons that can be readily pulled from this molecule down here, the one over here? Which protons are those? Which protons are those? This must mean something that I'm not familiar with. Which protons are those? The ones next to the... Oh, brother, come on, you! The ones next to the carbonyl group here. So there are 2 hydrogens in there, right? And either of those 2 hydrogens can be readily transferred to an appropriately strong base. Why? Well, because the anion that we create will be very nicely stabilized through resonance with a carbonyl. Create an enolate. So we know that this thing is going to pull a proton away from there. Do you remember what the pKa of the conjugate acid of this might be? That is the pKa of the NH form of that. It's about 37. What about the pKa of these protons in here, give or take? It's about 25 or so. That's an ester, right? It's a cyclic ester, so-called lactone, but still an ester. It's about 25. So if the pKa of these is 25, and the pKa of the NH compound there is 37, what kind of KEQ do we anticipate in here? Well, some ridiculous number of the order of 10 to the 12, something like that, right? So, upon exposure to that LDA thing, this ester will be converted entirely, completely, irreversibly, utterly, hopelessly into the corresponding anion. Let me switch for a second to the document camera here and draw you a little cartoon of that anion to understand what may be happening when we go in then and toss this bromoethane at it. Let's imagine that this the ring structure were more or less planar. We know that it's not perfectly planar, but for the sake of the discussion, that's a good enough approximation. So here it is, OCH3. I'm not sure what the hell that OCH3 is doing there, but anyway. So here is a geometric plane containing the molecule. That's the carbon which has undergone the deprotonation. The carbon formally sustains a negative charge. There is a pair of electrons there. These electrons, of course, are resonance delocalized into the carbonyl for all those reasons that we discussed in the past. So far, so good, right? Now, the moment that we toss some iodoethane, some bromoethane rather, at this molecule, we perceive that the molecule of bromoethane could interact with the anionic and consequently nucleophilic carbon by approaching it from the top face of that plane containing the ring, as well as from the bottom face of the plane containing the ring. And again, we may argue, barring effects that we are not aware of, do we perceive any reason why the bromoethane should prefer to approach from the top face as opposed to the bottom face? Do we see any reason why that should be? It's hard to imagine a reason, at least based on what we know. So we will have to conclude, on the basis of our knowledge, we anticipate that the incoming alkyl halide may react with the nucleophilic carbon of the enoid, either by approaching it from the top or from the bottom. If the reaction were to occur so that the halide comes in from the top, well, the ethyl group, this is for the top phase approach, then the ethyl group would connect to the upper phase of that carbon framework, the ring, and we will create a structure that looks like that. Do you agree? But if the ethyl group were to approach from the bottom, we would create a slightly different molecule, slightly different product, one which now ends up looking like such. H, like that. OCH3, H. Right? That's what will happen. What's the difference between these two things? Well, in one case, you may say the ethyl group has arrived with a cis relationship relative to that CH3O containing branch. In the second case, bottom phase attack, the ethyl group has connected with the trans relationship relative to the pre-existing ring branch. Yeah? Now, if we had to describe these two structures that in principle we envision as potential products, we will have to describe them as what? What's the relationship between those two things? Those are diastereomers, because they're definitely stereoisomers, but most definitely they're not mirror images. So they're diastereomers. By definition, diastereomers are stereoisomers, they're not mirror images. But then, back to the question in here, if I may switch back to the document, to the PC, from document camera to PC, we would have to write in the structures of both expected products. And here they are. Shall we say the cis and the trans diastereotic form of the material. All right? Great. You may appreciate, again, the similarity between this exercise and some of the exercises in the previous worksheet, number 11. Any questions or comments about this? Seems to be more of the same, right? Let's see what can be done in here. We take this enantiomer of the alcohol, and we treat it with, what's that? Sodium hydride. What is the chemical reactivity of this thing here? It's a very strong base. What is this going to do to that? It's going to pull the proton off the alcohol because the pKa of the alcohol is somewhere around 16 or so. The pKa of hydrogen, which would be the conjugate base of sodium hydride, is about 40. Yeah, but anyway, it's very large. About 40 or so. So again, the difference in pKa is so enormously vast that there is no coming back in here. Sodium hydride pulls a proton, and then hydrogen flies away, and that's the end of the story. But that means that upon treatment with sodium hydride, we create an oxygen anion. And we know that these oxygen anions are apt to participate in nucleophilic reactions, in SN2 type reactions. Do we see an opportunity for SN2 reaction here? Yes or no? Well, hell yes, look what's on the other side. In alkyl bromide, this alkyl bromide is drawn in an extended conformation. So as drawn, this bromine will be way too far away from the O-. But we recognize that all of these bonds are single bonds. So the molecule can undergo completely free internal rotation about all these single bonds. Imagine this molecule undergoing this rotation and at some point acquiring a conformation in which the oxygen comes sufficiently close to the backside of the carbon-bromine bond to perform the SN2 reaction. Well, obviously, an SN2 reaction will occur, driven by the great decrease in basicity of the system. We destroy an alkoxide pKa about 16. We create a bromide pKa on the conjugate acids about -8 or so. So huge, immense driving force exists. And the result will be the formation of this oxygen-carbon bond, again, by an SN2 process. Lo and behold, we create again an ether, a cyclic ether. All right? See how similar this is to the reactions that we have seen in the previous worksheet. That's why I'm doing these first. Okay, I believe that there's going to be one more, and this also is suspiciously similar to something that we have seen in the very recent past, that we have seen actually last Wednesday. What is this business in here? KOCH3. Well, that's the potassium salt, K+, of OCH3 with a minus on the oxygen. What is CH3O minus? What is it? It's the conjugate base, or what? Of methanol, CH3OH. The conjugate base, maybe I should quiet down because I may be bothering your friend who is texting. I apologize for any inconvenience, but I got an exercise to do. Is it okay if I continue? I'm not disturbing you, am I not? Am I? Great, thank you. Now, the CH3O minus is the conjugate base of ethanol, or methanol. And what kind of pKa do we associate with methanol? About 16, so it's a pretty strong base. If we have CH3O minus, well, in a chemical context, they may either function as a base or perhaps as a nucleophile. Given the substrate which is given to us, this, let's see what kind of chemical reactivity is likely to occur here. Do we recognize any features of this molecule that might provide a hint as to what may be going on? The esters. Do you remember what we have called this type of diester last time. I gave you the name of that. Let's call it malonate, right? Let's not forget that there is a hydrogen here, yeah? And look, I'm sorry, I'm a man of the last century, and I am really sorry about this. But I think it's unbelievably rude to come to class and text while I'm talking. It's unbelievably rude. What would you think if I came to class and instead of lecturing, I texted? So put those telephones away and listen up. You're here, you're paying for this, to listen to me, not to text. That's rude. Okay? Good. Now, what is the pKa of this hydrogen? What? What? So, if we had only one ester in there, what would be the pKa of that? It'd be about 25. With two esters, it's going to be about what? So I guess it's going to be around 14. Now, we have the conjugate base of an alcohol, yeah, with a pKa of about 16. And here we have a modestly acidic CH bond with a pKa of about 14 or so. Your bet, what's the fastest type of chemical reaction that could possibly occur when we bring this material here together with the methoxide? Deprotonation, absolutely. Whereas methoxide, yeah, can and does function as a nucleophile SN2 reaction. In this particular case, we perceive an opportunity for deprotonation, a very, very fast reaction. So, if I can switch back for a second to the document camera, we may infer, based on everything that we have said in the past, that the material in question, this malonate, so-called, yeah, will undergo rapid deprotonation. The methoxide ion will take that proton away from this material pKa approximately 14, yeah, and cause a formation of the corresponding enolate, something that we describe as such. Dot dot minus COO CH3 COO CH3. Here's the pair of electrons left on the carbon following deprotonation. The pair of electrons, of course, is delocalized all over those carbonyls. Nonetheless, some electronic density remains on this carbon, and as we know, these enolates, in fact, behave rather well as nucleophiles in SN2 reactions. But now, we also notice that within the same molecule, there is a carbon-bromine bond in here. And so we immediately recognize an opportunity for this enolate to engage the carbon-bromine bond in an SN2 reaction. We may furthermore infer that because the SN2 reaction entails the attack of the enolate into the anti-bonding orbital associated with a carbon-bromine bond, the SN2 process must cause inversion of configuration of this halogen-bearing carbon, meaning the enolate must connect to that carbon atom with the orientation opposite that of the original bromine. Yeah? When we do that, we can do that with molecular models, or if you have been using molecular models in the recent past, you can probably picture in your mind that this SN2 process is going to cause the bromine to go away, the hydrogen to come to the front, and the product to form with this particular configuration here. Here is the hydrogen. That is the malonyl fragment. 1, 2, 3, 4, and 5. That's right. COO CH3. CH3OOC, we anticipate that the displacement now proceeds with inversion of configuration of that carbon for all the reasons that we have addressed in the past. Again, on the previous exercise, we had a very, very similar problem. And I hope you remember that from last Wednesday. So, we can complete this diagram by drawing in the product that I had just created on the paper here. And there it is. That's the one. Okay? The reacting center obviously has undergone substitution with inversion of configuration. Okay? Any questions or comments about this? You may sense, correctly so, that it's always the same story. You know, once we understand exactly how these reactions go, attacking to the backside because of acceptance of electron density into the carbon halogen and the bonding orbitals, and so well, everything else follows once we understand these reactions at the electronic level. Yes?
Would this reaction still be possible if there was a double bond, like halfway between Br and diester chain?
Somewhere in here?
Yeah.
That's a very interesting question. Let's address that. Now, you may appreciate that in the product, these 4 carbons, 1, 2, 3, and 4, must acquire, shall we say, a U-type shape. Do you agree? That means that if we had a double bond somewhere in here, a double bond of cis or Z or Z configuration, then the reaction will still work. In Europe, because the double bond of Z or Z configuration will pop up in here and will force the carbon atoms to acquire this U-type shape. But suppose that we had an E-type or trans-type double bond in there. We ask ourselves, would a reaction still be possible? Well, let's consider that. In your opinion, how easy might it be to force a 5-member ring to sustain a trans double bond? It's impossible. If we make a model, we would perceive that it is simply not possible to create a 5-member ring, or a small size ring anyway, with a trans double bond. We can't. If we were to put, say, a trans double bond here, okay, between that carbon and this carbon, then the trans double bond will pop up at this position of the product. It is simply not possible for their ring to sustain a trans double bond. Unless there were a mechanism for the double bond to undergo isomerization from trans to cis, there will be no possibility anymore for SN2 reaction, because it will not be possible anymore for the nucleophilic end of the molecule to interact with the electrophilic end of the molecule. Do you find this convincing? So now, there is one more comment. As I said, nothing will happen unless there were a mechanism for isomerization of the double bonds. Do we know of any sensible mechanisms that might cause isomerization of double bonds? Cis to trans isomerization? Not quite. Do we know of any ways to isomerize double bonds from cis to trans or trans to cis? Do we? How do you do that? First you have to break it. And how much energy does it cost? It costs about 60 kcal per mole. Right? To break a double bond, for instance, thermally, you need about 500 degrees C. So you have to cook your molecule to about 500 degrees C to put enough energy in there that the double bond breaks and starts working. But at that temperature, other things that you have around the molecule risk breaking up. Right? So, to the best of our knowledge, or at least at this point of our knowledge, we are unaware of any methods to cause an isomerization of a double bond from E to Z or cis trans. Right? We don't know how to do that. We may infer that if there were a double bond in here, then arguably nothing sensible will happen. At least nothing within the scope of our present knowledge. Yeah? Okay? And I guess on the note, we can conclude. We will finish this off next time.